I'm kind of going a little bit off of, chapter 2 here. I skip and I put everything in chapter 4 that deals with bonding and water and things like that that aren't ionic bonds. So the whole reason that, and again, while I'm talking, you have a question while we're doing stuff here, type it in the chat. Let me know. I'll slow down, I'll stop, I'll go over whatever here. Just like if we were in the classroom. So, why do atoms bond? Okay, the big reason is they want to lower their potential energy. So all of our atoms, as you know, have valence electrons based on where they are on the periodic table. They want to be like a noble gas. My metals want to give up electrons if they can to be like a noble gas. My non-metals want to gain electrons so they can look like the noble gas that's coming up. But by doing so and becoming a noble gas and having that happy magic octet 8, they no longer want to bond. I mean, yes, the bigger ones we can force to bond and things like that, but for the most part, they're content. So our goal is to lower our potential energy, and the way we do that is all based on, okay, how we bond. So there's three types of what we call intramolecular bonds, the things that essentially make compounds. The ionic bonds we've already talked about. And 99% of the time, they're between a metal and a non-metal. And we're going to talk about something called covalent bonds, and we're going to talk about something called metallic bonds. Okay? We're very generally going to talk about metallic bonds here. Okay? Very, very general, just for completeness. We've already talked about ionic bonds. We're going to focus on covalent bonds. Okay? So I'm going to go back to the live cam and use some board here, board action. So in an ionic bond, you have a metal and a non-metal. So again, remember on your periodic table for my metals and my non-metals, for groups 1, 2, 13 through essentially 18, but since we're not talking about 18 bonding, 1, 2, 13 through 17. The number in the ones position tells me how many valence electrons I have. All right, so let's say we have, let's start with our simple sodium chloride. Okay, we have sodium. Sodium's in group 1. Sodium has 1 valence electron. Chlorine is in group 17, the halogens. Chlorine has 7 valence electrons. Okay, sodium wants to lose 1, give up its electron, and look like neon. Chlorine wants to gain an electron and look like argon. Okay, on your periodic table. So sodium says, here, chlorine, I really don't want that electron. Chlorine says, I will gladly take it. Sodium, all right, looks and is now positive because, again, I lost 1, but I lost the negative, so I become positive. Chlorine gains 1, and it's gaining, yes, but it's gaining a negative electron, so therefore chlorine becomes negatively charged. And the positive and the negative are what makes sodium chloride come together. Okay? We talked about that. It's a transfer of an electron. Okay? But what happens if I have something like, let's say 2 chlorines together? Because we know that chlorine's a diatomic element, and chlorine exists in nature as Cl2. Well, if I look at chlorine, okay, and I look at another chlorine, chlorine has 7, chlorine has 7. Now each chlorine wants to gain 1. None of them want to lose. So this chlorine wants to gain 1, and this chlorine wants to gain 1. Over here, we had something that wanted to lose and something that wanted to gain. Here we have something that wants to gain. Both of them want to gain. So what happens? Neither one's going to give up 1, so an ionic bond really isn't going to happen. What's going to happen is chlorine's going to look at the other chlorine and say, hey, we both want to be happy, and we can complete this happiness if we share our electrons. So in an ionic bond, you have a complete transfer, and over here, we've got a sharing of our electrons. Okay. So what happens is that this chlorine sees 1, 2, 3, 4, 5, 6, 7, that one there, 8 as its own. Happy magic 8. 1, 2, 3, 4, 5, 6, 7, that one there, 8 as its own. So it'd be like if I handed you a $100 bill. Over here, I hand you the $100 bill. I walk away. I no longer have $100. You have $100. Here I hand you a $100 bill, but I don't let go. In your mind, you have the $100. In my mind, I still have the $100. Okay? Now we represent that by a line. The line means 2 bonding electrons. Okay? I have 2 bonding, or what we call shared electrons, bonding or shared, and these are called non-bonding, lone, or unshared electrons, the ones that are just occupying space and not bonded up with anything. Okay. Now this is a special type of bond, seen usually 99% of the time. Again, there's always exceptions, between 2 nonmetals or 2 things that want to gain electrons, and we call it a covalent bond. And that is 100% a V, not a U, but it's a covalent bond. Okay. All right, so let's look at another covalent bond. Let's look at oxygen. Oxygen's in group 16. It has 6 valence electrons. Okay? Now, each oxygen is short 2 electrons. Okay? Which means that I need to bond twice in order to achieve that magic happy 8 and look like neon coming up. So what oxygen does is say, well, I got 6. I see you over here. I'll share here. I'll share here. And by doing so, oxygen says, well, I've got 1, 2, 3, 4, 5, 6 of my own. 7, 8. I've got 1, 2, 3, 4, 5, 6, 7, 8. So each oxygen is now happy. See, the corniness doesn't end just because I'm at home. Now, the way we represent this is by 2 lines. So each line is a shared electron and represents 2 of them, what we call shared pairs. So oxygen makes what we know as a double bond. Okay. And we'll talk about one more here. We'll talk about good old nitrogen. Nitrogen needs to share 3 times here, here, and way around town. And when it does, nitrogen forms a triple bond. Okay. Now, how many bonds I make is called my bond order. Okay, so bond order is the number of covalent bonds. So this would have a bond order of 3. This would be a bond order of 2. This would be a bond order of 1 for the chlorine. Okay. All right, questions on covalent bond here? Or is everybody sleeping? Okay. Cool beans. We'll keep moving on then. All right, so we're still going to stick with covalent bonds. I'm just going to erase this and move on. So we have single bonds, double bonds, and we've got triple bonds that could happen. And those of you who have to take Chem 2 and then eventually organic, carbon is one that can make 4 bonds. But see, here's the deal. If I can make 4 bonds, I can never make 4 bonds. There's nothing called like a quad bond or a tetra bond or something like that. I can make 3 bonds at most for our intents and purposes right now. Okay? For like carbon and things like that. There are other situations where, of course, I can make more bonds, but for our intents and purposes right now, I can't make more than 3 bonds to one thing, is how I'll word that. Okay? But I could make more bonds. All right, so we had chlorine bonded to chlorine. And let's look at another molecule. I want to look at hydrogen chloride. Hydrogen has 1 electron. It really doesn't want to give it up. If it does, it's just a proton. So what hydrogen does, and if you want to do it that way to remind you, like kind of connect the dots, there's the bond that's going to be made. And it's also a covalent bond. It's a sharing. It's a bond order of 1. But here's the deal with covalent bonds. Okay. First of all, here's the deal with covalent bonds. The hashtag for my wedding was this. So when I say I'm a nerd, okay, I really am a nerd. So when my wife and I were thinking of a hashtag, she brought that up, and I was like, oh my God, how did we not think of that? But here's the deal. Just like in this marriage here, you would think a sharing would be 50-50. But in reality, that's not always the case. Okay? Which I'm learning. And I'm still learning. Okay? Sometimes these molecules, or atoms I should say, that are bonding and forming these molecules, the sharing is not equal. Okay? It'd be like, hey, you and I are going to share a pizza. You might think you're entitled to half the tray, but let's be serious here. You're probably not going to get half a tray of pizza if you're sitting down eating with me. All right? So, I mean, let's be real. So, how can I tell if there is a difference, or how do I know that, this stuff isn't working out correctly? Evenly, I should say, not correctly, but evenly 50-50. And there's a term, okay? And the term is electronegativity. Okay? And this is on the slides, and I'm moving ahead a little bit. But electronegativity's definition, if we want to sum it up very generally, is my want or desire for shared electrons. How bad do I want shared electrons? Okay. And the way I tell how bad I want the shared electrons is I look at my main group elements. Now remember, again, main group is 1, 2, 13 through 17 for our intents and purposes, because as it says here on the bottom, noble gases are not considered because they rarely make bonds. But if I'm looking at my main group elements, my electronegativity, and transitions are weird, and we'll talk more about transitions in Chapter 14 in Chem 2 for those of you who have to take Chem 2. But electronegativity increases, okay? Let me get my little pen. Let's get a pen here. It increases as I move across. Okay? So this is an increase. I'm just going to do that because writing with a mouse is impossible. Well, maybe I could write increase. We'll make my my arrow into that. Let's try increase. How about INC? So I increase as I move across a period. And I increase as I move up a group. So the want or desire for shared electrons increases as I move across a period. 4, 1, 2, 13 through 17. Forget about the ones that are sitting down there, 3 through 12. Forget about them. Don't worry about them. Like I said, we'll worry about them in the future. Increase as I move across, increase as I move up, which means, okay, that fluorine is my most electronegative atom. It has the strongest want or desire for electrons. And for our intents and purposes, cesium. I know francium's below, but francium is radioactive. We really don't worry about that. This is the least. God, I hate writing with a mouse. That's not too bad, though. Electronegative. Okay? So what does that mean? All right, what does that mean when we're forming a bond? Well, what that means is this. That there's a tug of war for the shared electrons between the atoms. And if there's a difference that is greater between them in electronegativity. So for instance, chlorine is on the right-hand side of the periodic table. Hydrogen's on the left side. And there's exact numbers where you could sit there and calculate electronegativity and differences, and it could predict what type of bond you expect to see and which ones you don't, and which ones you do. But we're not going to worry about calculating them right now. What we're just going to worry about is there a difference in electronegativity? So chlorine's in a tug of war against chlorine. Well, chlorine's pulling with some electronegativity, and the other chlorine's pulling with the same amount of electronegativity. And since they're pulling with the same amounts of electronegativity, no one's winning the tug of war. So this one is actual equal sharing. However, we come over here, chlorine's on the right-hand side of the periodic table, very electronegative. Hydrogen's on the left-hand side, not so electronegative. And if I were going to draw these shared electrons, they would look something like this. And I'm over-exaggerating it to make a point. Here's my shared electrons. And chlorine is pulling them away from hydrogen. You're in a tug of war against a first grader. You are chlorine. You are pulling on the rope. Hydrogen's the first grader. You could pull the rope closer and closer to you, dragging that first grader around, but the first grader doesn't let go. That first grader's poor hydrogen hanging on. So the more electronegative atom actually pulls those shared electrons a little bit closer to it than 50-50. And depending on what the difference is, will determine, all right, how much it pulls and how close. However, by doing so, what chlorine does, or what happens in this bond, chlorine becomes partially negative. And that's a lowercase delta sign. It's kind of like an S with a fancy little curl at the end. The more electronegative atom pulls the electrons and gives itself It's not a full-blown charge. It's not like I gave up an electron and gained an electron like sodium with chlorine. But it's a slight charge. And by doing so, hydrogen gets a partial positive charge. Sometimes they show them like this. An arrow with the positive sign through it on the positive end. Now both of these are covalent bonds. But what I've created here, by having this slight shift in those electrons because of the electronegativity, what I've created is a pole. A pole is opposite charges, all right, over a distance. So if there's a difference in electronegativity, a right-hand side with a left-hand side, that's a covalent bond. Then we call it a polar covalent bond. If I don't have a difference in electronegativity, all right, I didn't create a pole. So we call it a nonpolar covalent bond. Yeah, leave this water out of the camera view. Questions on the difference between a polar and nonpolar covalent bond, or a covalent bond in general? Because these polar covalent bonds are what's going to make the aqueous solution chapter we are doing very, very, very important. So the question is then, why do things dissolve in water? Why are we able to do the molarity, and what is happening there? And it all has to do with water itself. Okay. Water is essentially an oxygen bonded to two hydrogens, where the oxygen is using two of its electrons, one to each hydrogen, to make the bond. Now, if we go back and look at our periodic table, okay, and let me click here, and we look at oxygens here, hydrogens over here, oxygen's more electronegative. Oxygen's going to pull those electrons towards itself. If I were going to draw the arrow, it would look something like that. With the oxygen getting the electrons, or if you wanted to draw them literally on the bond, like that, where oxygen's winning the tug of war. And by doing so, oxygen becomes partially negative, hydrogens become partially positive, so we have a polar covalent bond. Now this is important, because there's a rule of thumb out there that basically tells you the following. Likes dissolve likes. Meaning that like compounds dissolve or other like compounds. So polar compounds will dissolve polar compounds. Nonpolar compounds will dissolve nonpolar. Nonpolar won't dissolve in polar compounds. So car wax is a nonpolar substance. It doesn't dissolve in water. Okay, so, but my salts have charges like sodium chloride or potassium bromide. My ionic compounds have charges, which makes them polar. Okay, so where that's going to lead us here. I want to make a solution. I take sodium chloride, potassium bromide, whatever it is, and I place it into water. The potassium bromide disappears. The sodium chloride disappears. Magic. I have this powder, I place it into the water, and it disappears. Okay? Well, why does it disappear? Okay, so here we go. We're opening a new nightclub. It's a very popular nightclub in very smart areas. It is called Club Beaker. Okay, very popular nightclub called Club Beaker. Now, it's opening night at Club Beaker. And we want to make a splash. So we invite two popular rappers, an East Coast rapper and a West Coast rapper. The East Coast rapper, all right, is chlorine, and the West Coast is sodium. Now, we know what happens when East Coast meets West Coast. They collide, okay? Tupac gets shot, and that's my claim to fame, because Tupac got shot on Colville Lane in Vegas, and if you don't believe me, you can look it up, but it literally is Colville Lane, so whenever I'm out in Vegas, I always get a picture next to the sign. I know. Again, I told you guys I'm a nerd. So again, we're talking about Club Beaker. So outside the club, sodium and chlorine are stuck together fighting with one another. But this will be really bad publicity if this happens in our club. So we hire some bodyguards to escort both rappers through the club so everyone has a good time and we don't have to worry about anything. And the people we hire are water molecules. Now, we have to remember that, and again, just for completeness, I'll put the lone pairs up there so no one could yell at me in the comments, which I will disable, because I don't need that negativity in my life. All right, so we got partially negative, partially positive, partially positive, partially negative, and partial positive, partial positive, partial positive, partial negative, partial positive. You get the point. When sodium and chlorine enter the club, the water molecules instantly surround them. Specifically, they make hydrogen bonds. They make bonds. The hydrogen bonds up that chlorine. Sodium might interact with the negatives of the oxygen. Doesn't necessarily have to, but it'll be in there. Okay, and the chlorines again are going to float around and blah, blah, blah. But they're being separated by the water molecules. And the reason the water molecules can do this is because they make a polar covalent bond. Okay. So since they make a polar covalent bond, they have a partial charge. Their partial positive charge likes to surround the negative of the ionic bond and allows them to move freely throughout Club Beaker. Now I evaporate the water off and boom, they're back together. The sodium is back with the chlorine, and then I add some water and they're separated again. Okay? So how many of you ever had your parents tell you, get out of the swimming pool during a lightning storm because water conducts electricity? Yep. We've all heard it before. Well, the truth of the matter is, if they said it was because of the water, they're, I don't want you running back and saying they're not right, or they're right, or whatever, or they're wrong, or I'm saying they're wrong, or however you want to word it here. But the truth of the matter is, water doesn't conduct electricity. Okay? Neither does sodium chloride. What conducts electricity is the sodium chloride in the water. So they're correct for telling you, get out of the water. Okay? They're correct for telling you that, but it's not because water conducts electricity, because water doesn't. And sodium chloride doesn't conduct electricity because all the positives and negatives are bound up to one another. What allows electrical current to flow is the sodium chloride ions being separated in the water. Therefore, they're set charges, so the electrical current can flow. So whether it's the chlorine from cleaning the swimming pool, or it's the sodium and chlorine and potassium that's coming out in your sweat or your pee when you pee in the pool, because you all do it. And I'm going to tell you that it really doesn't matter because it'll be so diluted, and the ions, and I know everybody's going to say that's gross or whatever, but there's no way they could detect if you peed in the pool. All right, and I get it from a hygiene standpoint, but from an ion standpoint, those ions are already present in there because you're sweating and all of that fun stuff anyway. Okay, that came from your skin. So again, I'm not advocating peeing in the pool, but we all know we've done it, especially if there's a cold breeze and you'll just get back down in the water and just do what you got to do. Okay, but that's what's conducting the electricity. This separation in club beaker of your ions by the water molecules. And the only reason water can do that, okay, is based on the fact that it makes polar covalent bonds. Okay? All right, questions about how water breaks down compounds in water. They lied to you, Mandy, if they told you that it would turn blue. Yes. In Grown Ups with Kevin James and Adam Sandler there's no way it could turn blue because those ions are already present. They'd have to test for urea. But it'd be so diluted it'd be hard to test for. All right. That's what you'll take away from today's lecture. Nothing else. And now it'll be immortalized in... so let's get high subscriptions on this so I can start making some extra money. And then I'll start putting product placement in there. So any questions so far? I've been going for about an hour now. I'm not going to keep you any, I'm not going to keep you an hour and 50, but I do want to get to a certain point. And as long as I get to that certain point and give you some homework, I'll be happy. Okay. So we're going to make a little flow chart and talk about what happens with a substance and place it into water. So we're going to start with substance. Okay? Whatever the substance is. We'll draw a little arrow here and say, does it dissolve in water? Okay, and we'll go this way, and we'll say yes. And we'll go this way, and we'll say no. If we go this way and we say no, okay, then what we have is something called a non-electrolyte. So the term electrolyte means, do I break into ions? So when Gatorade says it's filled with electrolytes, it means Do I break into ions? Do I break down? Do I dissolve in water, and how much of me breaks down? Okay. If I break down and 100% breaks down, we call this a strong electrolyte. If I break down and only partially break down, we call it a weak electrolyte. So a non-electrolyte, I don't care, a rock. A rock doesn't break down in water. I know it's ridiculous and it's a very simple, thing, but something that doesn't break down in water. A strong electrolyte completely breaks down, completely dissolves, sodium chloride, potassium bromide, so on. A weak electrolyte, sugar. Sugar doesn't break into ions. I need a lot of water to surround the sugar molecules. I can increase the heat so the water molecules speed up. That's one way to get my solubility better. But sugar doesn't give me my maximum amount of ions. So we call it a weak electrolyte. If I don't completely break down, I'm a weak electrolyte. If I completely break down, I'm a strong electrolyte. If I don't break down at all, I'm a non-electrolyte. But here's the thing. Just because I'm an ionic compound does not mean that I will completely break down. Okay? I'm looking for the slide I want you to become familiar with very soon. So, there is a table in the book. It's on slide 33 in this presentation, and a table in the book, page 159. Just because I'm an ionic compound doesn't mean I completely dissolve in a solution in water. Some molecules have strong enough bonds that water can't surround and break them down. And I'll show you it on the PowerPoint, and again, the book is page 159. But here it is on the PowerPoint. And they're called our solubility rules. And it basically tells you what's soluble in water and what's not. Now again, if we were taking an exam and lecture, I'd expect you to memorize these. And you should memorize them because if we're doing a multiple choice exam, you're not going to have time to look up every single question. So you should at least become familiar. And what these mean is, if I have these, I'm soluble. Ionic compounds that are soluble in water. And down here, if I contain this list, I'm not soluble, which means that when I'm placed into water, I will remain a solid. So I want you to become familiar with these because we're going to do something where we do a bunch of reactions with these, okay? And I want to make sure that you know what is going on, okay? Questions? Because I got one more thing and then I'm going to stop this lecture today.